Oh, okay. All right. So thanks for giving me a chance to talk today. So I'm going to tell you about some work which has been submitted this afternoon. It's actually been a marathon because there's another work which we know has at least some overlapping results with us. I know because I saw them talk about it at localization last week. So we've been scrambling to get our paper ready and they've got theirs. But so in my case, this is work done in collaboration with, I guess I can't use my pointer anymore. Work done in collaboration with Haoyu Guo, who's a postdoc at Cornell, his advisor, Xiaoming Jian, and actually my old PhD boss, who I haven't worked with in 20 years, Andreas Ludwig. So at least I can use this to advance, hopefully, or not. Oh, it's doing that Zoom thing where it doesn't. Okay. So we're all waiting for this brave new world of quantum computation and quantum information where we can all come and work in beautiful levitating electromagnetic shielded offices like this and program computers that look like this. Well, not exactly. This is from a science fiction series about quantum computing. Although if Rice wants to invest in yet another new building, here's a nice plan. You might want to do it. But at least what we can hope is to get some new interesting quantum mini-body dynamics. This thing is, oh, now it's working. Okay. So this is a workshop about entanglement, so I'm not going to say that much, but what is entanglement? Well, practically, it's a resource for doing quantum things, but also from the many-body perspective, it's a mechanism for thermalization. In fact, it's the mechanism for thermalization in generic quantum systems, which are quantum chaotic. And in such systems, it tends to spread ballistically, at least if the system is closed. You can also use entanglement to classify different types of quantum many-body states. So a ground state of a gap Hamiltonian will typically have an area law scaling of the entanglement. If you integrate out part of the system and you look at the entanglement scaling of the subsystem. Generic excited states, on the other hand, have a volume law entanglement density. That's kind of what you would expect from a thermal state. And then quantum critical ground states can have some kind of logarithmic violation of the area law. So they're almost area law, but a little bit more entanglement than that. So this talk is a talk about quantum many-body dynamics in a particular context. And I guess the idea is that this is the type of thing that you can naturally do with the existing quantum hardware. From my perspective, it's just a new place to do non-equilibrium quantum many-body dynamics. See, the idea is that you have a quantum circuit. Imagine I have a chain of qubits in one dimension, and I'm going to apply, say, 2-bit and single-bit gates going forward in time, say discrete time evolution or continuous time evolution, your choice. Now, if I start with a generic initial state, it could be a product state, it could be something more complicated. Because this is a general circuit, the idea is that as we evolve in time, we're going to develop volume law entanglement, right? So we're going to create some really scrambled, complicated many-body quantum state at the end of the evolution. But there was an idea going back to Matthew Fisher in about 2018 that, well, what if we intervene by making random measurements along the evolution of the circuit? Maybe we can slow down this entanglement spread and get something different. So the idea is that at each, after say each set of 2 qubit gates, I'm going to make some set of measurements, and I'm going to flip a coin to decide whether I make a measurement or not. And then every time I make a measurement, I record the outcome. And so the idea is that when I make a measurement, say I'm measuring the density, then I'm making a local projection, and that if I make enough such measurements from an entanglement point of view, I break the circuit up into disconnected patches. So certainly there should be some classical percolation limit that if I make enough measurements, I just break the system up in space-time, and then I would expect to have area law entanglement, which in the case of a one-dimensional circuit just means basically no entanglement. And so this was the idea due to Matthew Fisher and collaborators, this quantum Zeno effect. And so by now, there have been many works on this idea, most of them numerical, but also some of them using ideas from random circuit models. And the key idea is that you can have a new type of quantum phase transition between the area law scaling state that you get by making too many measurements and the volume law scaling state you get if you have general quantum chaotic dynamics. And in general, this new measurement-induced phase transition is not just classical percolation. You hit some real new quantum phase transition before you hit the geometric percolation threshold. Okay, so, and this is where it would be nice to have a pointer that worked, but I'll have to do it with this thing. So I need to introduce a little bit of the setup mathematically here. So the idea is, let's start with a density matrix, say a pure state density matrix, and we're going to implement this protocol. So I'm going to evolve with some initial time evolution, u of t1, that's the unitary dynamics. Then at time t1, I make a measurement, that's p1. Then I evolve, make a measurement, evolve, make a measurement, right? And then I can encode all of that information in this d of t, which is essentially the evolving density matrix. Now, this density matrix is what we call a particular quantum trajectory, which is to say, to write this thing down, I have to tell you what the measurement outcomes were every time I make one. That's what those projectors do, right? So this d of t thing, which is like my evolving density matrix, if you take its trace, there's actually interesting information encoded in its trace, which is to say it's actually the survival probability, according to the Born rule, for the circuit to survive this many measurements. So, for example, I evolve my initial state psi naught to time t1, I make a partial projective measurement, that gives me one Born probability, I evolve that state, I project to n2, and so on and so forth. So if I want to calculate entanglement, one of the difficult things about quantum information is that it's not usually extractable from things that are linear in the density matrix. Actually, this quantum Fisher information maybe is an exception. I don't understand it very well. But usually we have to look at something like powers of the density matrix. And by looking at powers, we can reconstruct the entanglement entropy. So say I want to calculate the nth power of the density matrix. I can actually get that by using this d thing. I just take n powers of d, and in order to normalize it properly, I'm going to have to divide by the trace of d to the n. And now I want to do an analytical calculation, which means I cannot make predictions for a particular history of outcomes because that's a random system. So instead, I'm going to average over all possible trajectories. That's what this bar means. But I have to weight the average correctly. That means I weight each trajectory according to its Born probability. Now, I'm a disorder physicist who spend way too much time of my life working on Anderson localization physics. And so one of the things you learn as a disorder physicist is if you want to do a disorder average at the beginning of your calculations, you can use a replica trick. And so that's what we're going to do. We're going to take not n copies of the density matrix, but r copies. And then if I just count here, I've got n copies, and an extra one. I can actually get what I want by taking a formal r goes to 1 limit at the end of the calculation. Okay, so that's the key idea. That's what makes it different from a disorder problem, in that we're taking the r goes to 1 limit instead of the r goes to 0 limit. Okay, so we have to calculate basically a replicated version of this d thing, which is my evolving density matrix. And it's a density matrix, so you evolve forward in time and you evolve backward in time. And I guess in the quantum info community, they like talking about this with respect to a doubled Hilbert space. I don't really understand how they think about things, but for me, I see a density matrix evolving in time, and that's the Keldysh formalism. That's what we use in condensed matter, right? Okay, so I can write a path integral to describe this time evolution. The price you pay when you use the Keldysh formalism is that you have particles on two separate contours. It's the part of the contour that goes forward in time and a part of the contour that goes backward in time. And I'm just trauterizing that part and that part separately. And now we're going to do this for a very simple fermion system. So I'm going to take, say, 3 fermions and 1 plus 1d. I'm going to add to it interactions. So this u is something like a short-range repulsive Hubbard u. There's a minus sign there because you get different signs on the two contours. And then this red thing, which is actually an upsilon, is coupling to the classical density that encodes weak measurements of the density. You can actually also do projective measurements if you want, you get the same answer. Okay. Yeah.
Those sides, the J is the replicate index.
J is the replicate index.
At the same point in space.
Yeah, so everything here is local in space and time. Well, except for the bare propagator, of course, these are propagating fermions. That's right. And so the measurements couple to all of the replicas in the same way. What they couple to is just the so-called classical density operator, just the average of the density on the two contours. Okay. So that's a microscopic formulation of this problem. But just like in Anderson localization, just staring at this horribly complicated action, you can already say something about the system from a symmetry point of view. And the key point is that if I ignore the interaction term, which is what everybody's done up until now, then if I look at just the free fermions and the measurements in a particular beta spaces in Keldysh, don't worry about it, then what you see is that this free fermion system has a huge amount of symmetry. Namely, I can make independent UR times UR rotations on the forward and backward Keldysh contours. Okay, but these are this asymmetry in this funny replicated space. And at the end of the day, we're going to have to take R to 1. So this is just like the type of construction that we're used to for building field theories of Anderson localized problems using generalized nonlinear sigma models. However, at the end of the day, something different must happen, which is that when I turn on the interactions actually reduce the symmetry hugely down to just the left and right permutation group on this index J. And also you preserve the charge U1 of each copy of the fermions is preserved as well. So what was already done before our work was to notice that this huge symmetry presumably implies some type of sigma model. And that's a standard idea from Anderson localization physics. So there was a paper, a PRX in 2023 by Sasha Merlin's group, where they take that fermion theory without interactions, integrate them out, find a saddle point, do a trace log expansion. At the end of the day, what you get is this field theory. So this is what looks like a quadratic action in terms of some bosonic field variable, but this bosonic field variable is a unitary matrix. So X dagger X is 1. And roughly speaking, you could think of this X as a product of fermions across the two contours. So one of them are, and this is, I should say, X here is an SUR matrix. X is the part of the theory that encodes entanglement. And I'll explain how by the end of the talk. There's an overall U1, which just describes the overall average density dynamics, which are diffusive and boring, so we're not going to talk about that. And one of the very strange things of this simple free fermion theory is that it looks like it's in Euclidean spacetime. But this is a circuit evolving in real time. So it turns out, and this is correct, there isn't a mistake here, the dynamics really do look like a Euclidean Laplacian, and this is coming from the simplification of the measurements. Another simplification of the measurements is that they wipe out the Fermi distribution function. So normally, if you study fermions out of equilibrium with interactions, this is the most horrible problem in the world. It's really hard to do anything except semi-classics like the kinetic equation. But here, there's a vast simplification, which is that the measurements heat the system and smear out the Fermi distribution function. As a result, you get this very simple description of free fermions. Even free fermions out of equilibrium is usually complicated because of the distribution function. There's no distribution function here. Okay, so you have this nice, simple sigma model theory. This is just a stat-mech model. You can go and do renormalization group on it. But unfortunately, this theory doesn't show any interesting dynamics. Namely, you can calculate the one-loop RG function for this coupling lambda. It's actually been known for forever. And it's just a constant with a fixed sign. And what that tells you is that the stiffness of the sigma model flows to 0, which implies that you only have an area law phase. And this is what we expected for free fermions. You don't actually, in order to get entanglement, volume law, you need interactions. Okay. So actually, there was work already that suggested for the particular system we're studying, where we have density-density interactions, and we're measuring the density, that there should be not 2 phases, but 3. So there should be an area law phase. That's what's called this purified phase over here. But then there should also be the volume law phase in terms of entanglement with 2 subphases, depending on whether the charge is so-called fuzzy or sharp. So the fuzzy phase means that by making density measurements, I cannot reconstruct what the total charge density of the system is. So imagine I initialize the circuit in a cat state of different density sectors. By making these measurements, I can't figure out what the actual density of the system is, or another way of saying it is I don't purify it into a state with a well-defined total charge. But on the other hand, for measurement rates above a certain threshold, but below what should be the measurement-induced phase transition, it's possible, at least according to this numerics and some effective field theory, to get this intermediate regime where the charge is sharp. So I have a well-defined total charge, but the entanglement is still volume law. So can we somehow recover this? So the key is to go back to the sigma model that we had for the free fermion case. And we know the interactions are going to break symmetry down to some permutation symmetry. But also we know that there should be this charge fuzzy and charge sharpened dynamics. And these previous papers by Roman Vasseur and company claim that the transition in between should be Kosterlitz-Thales. So that implies that somehow U1 degrees of freedom should be important here. And after all, we put density interactions into the microscopics. So actually a really cheap and easy way to get the full theory of the interacting circuit is the following trick. You just gauge the U1s associated to all these different replicates. So technically, you send the time derivative of x to the time derivative of x plus some difference of phases. These are phases that live on the time-ordered contour, the anti-time ordered contour. And now these are some auxiliary degrees of freedom that are going to implement density-density interactions. So we know how to do that in Keldysh. You add them with a certain Gaussian action, with repulsive Hubbard U, you integrate them out. And at the end of the day, you get this modified version of our sigma model. Okay, so it's got a couple of different pieces, and I'll try to describe them to you in turn. First of all, there is a difference of current operators. So there's like a J squared minus a J bar squared. The J operator is the current operator that represents replica rotations on the left or in the time ordered sector. J bar is in the anti-time ordered sector of Keldysh. So if you want, these are just some things with second derivatives that make the sigma model itself anisotropic. But then there's also this quartic term, and this is like a phi to the fourth mass term that reduces, well, actually, both of these terms eliminate the continuous symmetry. The mass term goes like the Hubbard U squared, and it looks like it gaps out the off-diagonal fluctuations, right? So if M becomes very large, then if you write this out, you'll see that it would prefer the system for X to become a diagonal matrix, except it's not quite that simple because that term is SR cross SR symmetric. So actually, it can either be a diagonal matrix or any permutation thereof. And also because X is complex valued, not only can it be a permutation matrix, there's also going to be some complex phases that come along for the ride. Okay, so that's a very formal argument for the structure of the theory. And those phases will play a role in the charge sharpening transition. You can also, though, do a full microscopic trace log expansion like a good many-body physicist. And then you actually start to see some physics, which again is analogous to Anderson localization. So in fact, these mass terms, you can realize them as arising from a combination of fermion self-energies and for the diagonal elements, vertex corrections. The self-energies here, what they're doing is they're cutting off the effects of the measurements. They're decohering the effects of the measurements, which want to push you into the area law phase. But for the diagonal elements, there are additional vertex corrections, which are there because of a ward identity. And so there's a perfect cancellation. And so this dephasing mechanism is not happening for the individual U1 degrees of freedom. Okay. So we have now our full effective field theory for interacting monitored fermions. And well, what do you do with a field theory? You can do renormalization group. So we can now study the RG, just do a weak coupling RG study for this interacting model. And we get beta functions for 3 couplings. So for the stiffness lambda, remember that was the only thing we had for the free fermion case. But now we also have this mass term. And then there's also the interaction strength. And this gamma bar U is basically the same as gamma U. It's just divided by, divided by lambda. And so there's a whole bunch of terms here, but let me just highlight the most important ones. So number one, the interactions boost the stiffness. So that's pushing you back towards the volume law phase. It's almost like an Altshuler-Aronov type correction. It tells you that the interactions are generating entanglement. For the mass term, there are 2 important effects. Number one, the interference effects in the sigma model suppress the mass. So if the stiffness is small enough to begin with, I can suppress this mass in principle to 0 and still flow into the area law phase. The other important thing is that this mass term, you can think of it as we generated it from some trace log expansion or from this formal trick I showed you before. But the point is that even if I fine tune it to 0, it gets generated by the RG anyway. These current interactions generate it. Okay. So I can translate that. Yeah.
So R is disappearing here, so you're already taking somehow the limit of R to 1?
Yeah, that's right. So we have in the paper, which should appear whatever tomorrow, we have the full beta functions as a function of R, but then we just take the R goes to 1 limit. So for example, that -1/pi, that's the R goes to 1 limit of the free fermion case that I showed before. Some of these terms depend on R, others don't. Actually, there's one number here that we don't know for general R. We have this for R equals 2, but for some technical reasons, it's very difficult to calculate for general R.
Well, you really need to do this for all integer R.
You have to do it for all R. You have to do it for all
Do you
R.
trust this for all R? Is the RG okay for all integer?
Well, in all of the corresponding systems in disordered physics, where you can do perturbation theory, so in disordered physics, we have other methods that we can use. We have a supersymmetry method. We actually have a Keldysh method. And whenever you're doing perturbation theory, they always agree. Now, for these monitored fermions, I don't know if we have any other methods, right? But at least the physics that comes out is what we expect. So here is a plot of the RG. So we had 3 different couplings: the stiffness, the interaction coupling, and the mass. But I'm just going to set the interaction coupling to 0 and just plot the RG flow as a function of the mass and the measurement rate. So lambda inverse is like the measurement rate, lambda is like the measurement lifetime. And so if I don't have interactions, then I just have a slow logarithmic flow to the area law phase. If, on the other hand, I turn on the mass, I have strong enough interaction that I very rapidly flow towards the volume law phase. And the effect of that mass is going to be to kill everything except the U1 fluctuations, which are exactly going to be the U1 terms that are responsible for charge sharpening. And then finally, there's some kind of separatrix in the RG flow, and that's again due to the mass being suppressed by these interference effects. So we don't, unfortunately, have a fixed point within the weak coupling RG, but at least you can see some kind of separatrix, which indicates there should be a separation between the volume and area law phases. Now, we can also apply an order parameter description of the system. How much time do I have?
Including questions, you have 7 minutes.
Okay, I'm doing fine. So, all right. So we can also use this X field, this unitary matrix field, in order to now come up with an order parameter description for the volume law phase, the area law phase, and also distinguishing these 2 subphases of the volume law phase. Okay? So in particular, to distinguish the volume and area law phases, turns out you don't want to use X itself. You want to use its modulus square. And the reason is that X is a unitary matrix, so it has complex phases that can fluctuate. So if you want to simply know whether you're going into the volume or area law phase, in all of the previous work done on measurement-induced phase transitions and mapping them to effective statistical mechanics models, that transition is always characterized by the breakdown of SR plus SR replica symmetry, which here corresponds to the forward and backward Keldysh contours, down to a diagonal permutation subgroup. And that we can see in this X. So when that mass gets very large, the modulus of X wants to be, well, X wants to be a diagonal matrix. And so the modulus of X wants to be, say, the identity matrix. And that is a signal that we're going into the volume law phase. On the other hand, if we go to the area law phase, the X is going to fluctuate very strongly, and the expectation value of X and its modulus square will vanish. But we can also distinguish within the volume law itself the charge sharpened and charge fuzzy phases by thinking about the expectation value of X itself. So to see that, we can just enumerate these 3 phases that were talked about before and talk about how we can think about them in terms of the expectation value of either modulus X squared, so that's this V, or X itself. And so, for example, if I have the charge fuzzy volume law phase, that's the sort of most entangled, most fluctuating. I'm doing the least amount of measurements. In that case, I simply get an ordering of X. Okay, so X wants to be a diagonal matrix or a permutation thereof because of this huge mass parameter. But moreover, the diagonal elements are these vertex operators, e to the I some phases, and those phases are dual to the phases that measure charge. So if those order, then it means the electric charge is fluctuating like crazy, and that means I can't learn anything by making measurements. So this is the charge fuzzy phase. The area law phase corresponds to the opposite limit, where the X field itself is fluctuating like crazy and simply has zero expectation. But now there's an intermediate phase where the X field is fluctuating because of these phases, the U1 phases, and its expectation value vanishes. But this V, which is the modulus square of X, can still be a well-defined diagonal matrix where the phase fluctuations cancel out. And so that's what we associate to this charge sharpened volume law phase. And for all of these, the entanglement properties can be very easily thought of the same way they were in previous work by Andreas and Chaoming, which is just thinking about domain walls in these effective statistical mechanics models. So the simple idea is that X is an order parameter for the volume wall. So when X takes a non-zero value, this is like ferromagnetism in a Ising model. If you have ferromagnetism and you try to introduce a domain wall, so when you try to calculate entanglement entropy, it's like sort of putting a certain twisted boundary condition, and then you get a domain wall between two different regions of the sample, and it's the tension of the domain wall which makes this area law, which here just means growing linearly in the size of the system. Whereas in this phase, it's like a paramagnet, it's fluctuating very strongly, and it doesn't cost anything to introduce this twisted boundary condition. Okay, so in summary, we've derived an effective statistical mechanics model using either this funny gauging trick, or if you want a gory fourth order trace log expansion, starting from a microscopic description of fermions. So we go from this simple, nice symmetric principal chiral model to something involving some anisotropic deformation and a mass term. And the interactions reduce the symmetry, and then we can understand all three of these dynamical phases of entanglement in terms of certain order parameters that are expressed in terms of this X. And I guess, one corollary of this description is that, for example, you do not expect to be able to have charge fuzzy dynamics in the area law phase, because it's incompatible with describing things simply in terms of this X field. So let me just close with our putative phase diagram. So this is the schematic phase diagram where on the vertical axis is the interaction strength, and on the horizontal axis is the measurement strength. And there is a measurement-induced phase transition, which should have an exponential form like this, coming simply from the fact that this mass term is relevant in an RG sense, whereas the measurements are only growing logarithmically and marginally relevant. But actually, from the state of the system we have so far, we can't distinguish actually two different scenarios. So in principle, with respect to the charge sharpened and charge fuzzy and charge sharpened regimes, this is the charge fuzzy regime, the most entangled, the most scrambled. This is the charge sharpened regime. At the moment, we can't distinguish between two scenarios. One is that these are two separate transitions that come all the way down to arbitrarily small interaction and measurement strength. Another possibility is that they somehow merge, and then generally you would expect actually for this to be a first order transition, because these are phases with different orders. However, this is a disordered system, so it may be that you actually can't have a first order transition. We haven't thought about this too much, but generally first order transitions in low dimensions are smeared out by disorder. Okay, so that's it.
I remember from the non-interacting theory that it looks very much like 2D and localization.
That's right.
I was wondering if an analog of, return to the origin operation of the localization.
Yeah, so I mean, of course, you can calculate, the beta function for this non-interacting model, which is exactly this, by expanding this in terms of the coordinates, and you could interpret this coefficient from some diagram. right? It's some diagram that survives and the replica goes to one limit. But beyond that, it's a little bit hard to really understand what's going on because this matrix is this weird superposition of forward and backward fermions. I think a better way to probably try to get at that physics is to actually look at the interacting case. Because in the interacting case, you can start to see things that start to look like the infrared physics of Anderson localization. So for example, when you do this trace log expansion, you calculate this mass term. How does it arise via the brute force trace log expansion? And what you find is that it arises from this fermion self-energy, and the fermion self-energy is having exactly the same effect. It enters in just the same way that if I were calculating the dephasing of the Couperon in Anderson localization, it's arising in exactly the same way here. So maybe that starts to give us a way to think about these types of matrix modes as being some type of quantum interference processes. But we haven't developed that far yet.
What understanding do you have of the field theory?
Yeah, so almost none. So we have a concrete theory, here it is. But it flows off to strong coupling, so we can do the weak coupling RG. So I think as I mentioned to you, I mean, one of the interesting things about this RG is the following. And I think this is something our competitors may not have, I'm not sure. We'll see, their paper's going to appear. So this current interaction is just an anisotropy in the sigma model, whereas the mass term is a mass term, but strongly relevant flows away. The key point is that in weak coupling RG, we generate the mass term, even if we don't have it to begin with. So it's probably sufficient to study the theory without the mass. The theory without the mass is just a deformed two-dimensional principal chiral model. The principal chiral model without the deformation is integrable. So the combination of these two, if we add this anisotropy, can we say something? It's a deformation of an integrable theory, and by using, say, the beta ansatz or whatever, could we try to actually get a non-perturbative description of that critical point? It's a tough program. We don't know. It's not unitary. And in fact, yeah, so thanks for asking that. So this theory looks unitary, right? It just looks like an ordinary nonlinear sigma model. And this is a Euclidean type convention where it's e to the minus s. But notice the interactions here are actually coming with an I. The I is coming precisely because these interactions were inherited from the Keltish formulation of the interacting fermions. So it's a bit weird. It's definitely not unitary. I think it's not unitary already because you have to take R to 1, but it's also explicitly not unitary because the interactions come with an I. Well, probably 0, because it seems to be some variant of percolate, but it's not percolation. Right? So like the exponent is not 4/3, but it's probably some log CFT with, yeah.
Great. So maybe one more question, and Fabian, can you
does it matter if you make the measurement in real space versus momentum space? Is it condition?
That's a good question. I mean, so we only set up the field theory in real space. I don't know what it would look like to do it in momentum space because the interactions then become horribly non-local. Yeah, it would be an interesting question.